Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. And each of these volumes is available on Amazon.com, both in Kindle and in paperback format. And I think it's a good read in case you guys are interested in purchasing it. You can search either for my name, David Terrell, or for the title of the series, The Math Lovers Book. Anyway, that's a little plug for my book or my series. Today is Saturday, so I'm going to feature another biography of a famous mathematician. Throughout history, I have 80 of them listed at the end of volume 2 chronologically. I'm up to the 28th of them now, which is Colin Maclaurin, who lived from 1698 to 1746. And here's a picture of him on my bio in my book. And I think the thing he's most well known for is the Maclaurin series, which is really just a special case of the Taylor series. But I guess most of the Taylor series that mathematicians study, particularly when they're first learning calculus, are Maclaurin series. They're just Taylor series about x equals 0. But they don't have to be centered around the origin of x equals 0. Taylor series can be expanded about any point on the x-axis where the function is well defined and the series converges. But x equals 0 is just a special case. And here's 5 commonly studied Maclaurin series. I'm not going to go over them, but they're very useful. And you could derive them using basic calculus. And that wasn't the only thing he did, though. I mean, I think he did at least a couple other important things. One result I really liked from him, I guess he collaborated with Leonhard Euler, who's considered by many the greatest mathematician of all time. I'm going to get to him in a few weeks, but they came up with this pretty amazing formula, I think, for expanding a function, an integral defined by an arbitrary function. So if we want to expand an integral as a power series, and there's often special cases where we want to do this. Um, Here's a formula for it, and I guess S is an approximation. So you approximate your integral by a finite sum, kind of like a Riemann sum. That's easy to do. You just, your integral is a sum over, infinitely thin rectangles. But here we're just replacing it by finitely many finite width rectangles. But then you get an error, and you can actually come up with a series for the error that converges, and this can be very useful. Particularly, like one thing you can derive with this formula is Stirling's approximation for the factorial function, which is a very useful asymptotic series. I just thought I'd mention this. And another thing he did, I just learned this today actually. He came up with this result involving rotating oblate spheroids. You guys may know that the Earth is an oblate spheroid. It's not an exact sphere. It's flattened slightly at the poles. The eccentricity is about one 300th. It's very small. Uh, but basically, the diameter through the poles is about 30 miles less than the diameter through the equator. And the reason for this is because the Earth is rotating about its axis, and if the Earth was completely a fluid, I think it would be a lot more eccentric. Most of the Earth is solid, but there's other planets that are gaseous giants and gases and fluids, like Jupiter and Saturn, and they're a lot more eccentric than the Earth. I think Saturn has the highest eccentricity of any of our planets. It's about 1/16th, and I think Jupiter's like 1/25th. So I think you can even see when you look at photographs of Jupiter and Saturn. I think you can even tell that they're not exact spheres, that they're more kind of oval shape. And he came up with a formula for the rotation rate in terms of the eccentricity. So if you know the eccentricity of a perfect fluid, oblate spheroid shaped like a perfect fluid, you can actually calculate its rotational speed. Um, and I think it peaks when the eccentricity is about 0.92, when it's almost like a pancake, uh, which is kind of interesting to me. If it was completely a pancake, then it wouldn't need to be rotating. But anyway, so that's another result he came up with, which I think is kind of a cool result. And unfortunately, he didn't live very long. I think he only lived to be 48 years old, and he died of a condition known as dropsy. I don't even know what that is, but he had an accident where he fell off his horse shortly before he died. So that's how he died, which was pretty tragic. I guess he probably could have come up with a lot more useful results if he hadn't died so young. But anyway, that completes my profile on Maclaurin. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you guys next time. Bye.